Well, as always, as I ask each time, let me know if there's anything you want me to go over in particular. Otherwise, I'll work my way backwards through some of the homeworks, I think. Okay, so what did we ask you to do? 4.1. Okay, let's try it and see. 4.1. Verify that for all ordinals, alpha, the L rank of alpha is the same as the V rank of alpha is alpha. Prove that for all n less than or equal to omega, Ln equals Vn. So the answer is, can be quite short, right? So to recall, right, just to remind us. So this is the least alpha such that, well, the L rank of a set X, right, is the least alpha such that X is a member of L alpha plus 1. Contrast this with the V rank. This is the least alpha such that X is in V alpha plus 1. So we already know that the ordinals intersect V alpha alpha. And so the rank of alpha is just alpha. And we're being asked essentially to verify that the L rank of alpha is alpha. And basically, it's because we have this already for L in place of V. So the solution here for 1, right, can start out, well, you could remark, we already know this. And if you look at lemma 4.4, we know that the ordinals intersect L alpha, like for V, is also alpha here. So alpha is a subset of L alpha. It's a member of def L alpha. And if you wanted to justify that, I don't think you have to do this as part of your answer, but if you wanted to justify that, you could say, what is alpha? It's a set of x's in L alpha such that L alpha thinks this is an ordinal when I substitute in x for V0. So this makes alpha into def over L alpha. So alpha is in L alpha plus 1. So alpha is in L alpha plus 1. So this means that the L rank of alpha is less than or equal to alpha. So strictly speaking, you need to argue that it can't be smaller. Well, it can't be smaller because alpha is not a member of any smaller L betas. So the other direction. So we have what we wanted. The L rank of alpha is alpha, and that's the same as the V rank of alpha. Right, so that tells us what we want to know about, or what we've been asked in question 1, part 1. No. Okay, part 2, verify that the LNs are the VNs. Again, I have a feeling I may have said something similar to this already, but by induction on N. So for N equals 0, this is trivial. Okay, suppose it's true for K. Well, whatever is definable over LK, and here, it's contained in the power set of LK here. So as LK equals VK, right, here, this is just the power set of VK, which is VK plus 1. Right, so I use the induction hypothesis here. To say that VK is the same as LK. So LK plus 1 is contained in VK plus 1. And we need the reverse here. So pick something in here. So it's finite. In VK plus 1. Okay, again, this is the power set of VK. So all of these elements of this object in VK plus 1, these are all in VK, which is the same as LK. So X is a subset of LK. Okay. Well, again, as I say, it's VK. So now I just write down a definition for this subset of LK. So you could just quote the lemma that we already have, or actually an exercise that we already have. This was exercise 3.3. And that would then finish what we wanted. Any finite subset of a structure is definable. That's what this says here. And here's a finite subset of the structure. if you wanted to write a definition out, you'd say X is the collection of W's and now W has to be one of the Xi's. So we could just write this down. So V0 is V1, or V0 equals V2, or V0 equals Vn. And I'm going to substitute in here potential W's for V0 and X1 to Xn for the V1 to Vn. So as W varies over Lk, the ones that get picked up and make this true are just X1 up to Xn. Because it's either, to be true, it has to be either equal to X1 or X2 or X3 or anything up to Xn. So then this is in def Lk, which is Lk plus 1. So the X we picked out arbitrarily from Vk plus 1 is in Lk plus 1. Okay, and we're done there. So anybody want to ask anything there?
Hello, Philip,
Yeah.
can you hear me?
Yeah.
Hi. I had a wonder if we could just go over one of those last steps, because I don't really understand how again are we using the inductive hypothesis to get from def Lk to Vk? Or I feel like I'm being silly, but
That's all right. No, don't worry. Well, the inductive hypothesis is that we know that Lk equals Vk. What we're trying to do is show that Lk plus 1 equals Vk plus 1. This is what we want. Right? So what do you ever do in mathematics when you want to show two sets are equal? You show that one is a subset of the other and the other is a subset of the first. So that's what we're going to do here. So we're going to show, first of all, this direction, that
okay.
Lk plus 1 is a subset of Vk plus 1. So Lk plus 1 is this, def Lk. Well, everything that's definable over Lk is a subset of Lk.
Yeah.
So this is contained in here. And this is where the inductive hypothesis is used, because we assume we already know Lk equals Vk.
Okay.
So by
Okay.
definition, that's Vk plus 1.
All
So the
right.
inductive hypothesis gets used there, and it gets used down here as well, because we pick an arbitrary element of Vk plus 1, and we want it to be in here. So we pick an X in Vk plus 1, but to be in Vk plus 1 means it's a subset of Vk. So all of these guys here are in Vk. So here's me saying that. X is a subset of Vk. And again, the inductive hypothesis gets used here.
Okay.
Does that answer?
Yeah. That's
okay.
me.
Good. Okie doke. Is there anything you want me to go through that we've done in chapter 4? Because otherwise I'm going to go back to those exercises in chapter 3. But now would be a good opportunity to ask if you wanted me to go over anything in the lectures for chapter 4.
Could I quickly just get you to reiterate a comment, because you made a comment very quickly. I think it was in one of the recorded lectures where you were talking. Sorry, this is on page 47, in the form of formalizing definability.
Yes.
You talked about I think it was iota XUH, and you were saying something along the lines of H is being used to interpret X over the formula U, and you said it very quickly, and
Okay. Yeah.
I just
sure.
wanted to.
Okay, let's go over that definition again then. So, as you said, page 47. This is in lemma 318. This iota notation is, I confess, not used much, and perhaps I could have just done without it, but it is kind of useful. So in here, this is the structure we're interested in. This is the code of the formula. Right? And this is the valuation in the structure. So the idea is that maybe I've got this, that U is the code of some formula phi, and actually phi has got free variables V0 up to Vn. So the phrase I was using was that H, the valuation, we use to interpret the free variables in the structure X. So H of 0 up to H of n, right? This is a sequence of elements of X. Okay. So I can use these values to give some meaning to the free variables of the formula. So we interpret phi in X using the valuation H. Because now I've got my formula phi, and I'll put in for V0 up to Vn, here H0 up to Hn. So now I can associate some meaning to this. The formula says something now about these gadgets, right, here, which are all in X. And then the satisfaction relation just says how I can recursively define what it means for this valuation to make phi true in X here. And then the iota notation says, what are the things that I can put in for H0, keeping H1 to Hn fixed, that'll make this formula true in X. So this is going to be the collection of things in X here, such that the structure of X here with phi here, and these are the W's to be put in for V0, and then I've got H1 and up to Hn for the other things here. For W in X. So perhaps the phrase I was using was the valuation interprets the free variables of the formula, right, in the structure X.
Yeah, thanks.
Is that enough said about that? I mean, or you want to ask anything else?
No, it was. I think I understand now. It was just because you just made a quick comment about this is this is that, and this is the other. I was just
sure. I mean,
because it reminded me of vocabularies which I've done before, but I just wasn't sure whether it was a different way of talking about the same thing.
Right. No, it's the old story really, of the Tarskian satisfaction relation, which one does in logic courses. There's nothing. The only thing that's new around here is this kind of, well, the notation that we have to introduce to write it down, and this idea of coding, right? So this is kind of a new idea that one doesn't necessarily bother with in a logic course. But we're trying to formalize everything and do everything within set theory. So I need to have sets to correspond to my formulae.
Yeah, that's really helpful. Thank you.
Okay, good. Okay then. Well, let me primarily go through then those homeworks of 3, 4, 3, 5, and perhaps pick out something else unless you have things to ask or some other way of making the time more useful. Okay, let's look at 3, 4. There's 3, 4. So again, it's about the def function. Okay, page 48. And it wants us to finish 2 and 3 of, it should say lemma 319. It says 39. Yeah. Two and 3 of lemma 319 was left as an exercise. Yeah. Okay. So what was 2? Yeah. So if x was transitive, then we wanted x to be contained in def x. And 3 was, just the thing that I was talking about before. If I've got a finite subset of x, so the cardinality of z is less than omega, then z is itself, okay, so I've just done this already. So I don't need to do this again. So it's just the top one, which is kind of a simpler case of the bottom one. So solution, well, 3 we just did. And 2. So I pick an object in X and I want it to be definable. Well, what is Y? It's the set of its elements. It's a set of W such that X epsilon thinks now V0 is in V1. Well, I'm going to put in various W's for V0. But for V1, I'm going to put in Y. And W can vary over X. So this formalism just picks out those elements that are in Y. So here's the set of W's that make up Y. So this set is Y. So all we've done is just ensure that then this is definable over X here. And because we specified that X was transitive, this works. Because if Y is a member of X and X is transitive, Y is a subset of X. So all the elements of Y that we're concerned about to get them into Y are there in X because X is transitive. Right? So we have equality here because X is transitive. That's where we use the assumption that X is transitive. Right? If X didn't contain all the elements of Y, it would only pick up a proper subset of them. And then this would just be a subset of Y, and not all of Y. So we need the assumption that X is transitive there to do that. So 3.5. Right? If X is transitive, show that the def X is transitive. Show the def of X epsilon is transitive. I mean, sometimes I write def X epsilon, which is kind of very formal and precise, and other times I'm just a bit informal and write def X, because epsilon here is always to be understood. And then there are a couple of auxiliary questions. If Y and Z are in X, then is the unordered pair YZ in X? Sorry, def X. Or you could ask even more simply, is singleton X a member of def X? Well, to answer this first part here, you just have to, well, go to the definition and just show that we have transitivity. So pick something in def X. What do we want? We want it to be a subset. Okay, because Y is in def X, right, Y's got a definition of some kind. So some formula phi and some valuation so that Y is the collection of those things in X such that those elements make the formula true. W closed for V0 and then H1 up to Hn. And I'm letting the notation tell me it's implicit that the free variables of phi are within here for W in X. Right, so a fixed formula phi, a fixed valuation to tell me what to assign to the free variables. We let W vary. And somehow this definition, this valuation picks out y. So y here, obviously, right, is a subset of x by the nature of its definition here. And x itself is transitive. So again, rather like the last exercise, x is transitive. So what do I want to say? Y here. Y is a subset of x, right? But we know that x is a subset of def x here. That was the previous exercise, part 2. And this is what we wanted. Y is a subset of def x. It's almost, I don't need to write it out again, right? So we got what we wanted here. So what about these other questions? Okay, perhaps we've already seen this. Well, indeed we have. What is YZ? This is a finite subset of X. And we've already seen all finite subsets of the structure are in def X. So yes. On the other hand, singleton X, right, that's a bit different, right? Okay, we have that X is a member of def X. Right? It's the set of things that equal themselves. Just to labor the point. It's a collection of W's in X which equal themselves. Well, that's everything in X, so it's X. But that's not the same as that, of course. But X here in def X would imply that X is a member of X. Right? Which we can't have by the axiom of foundation. Right? Sets are not members of themselves. So in particular, I mean, I remark at the same time. So also, this is not in def X. This here, this is not in def X. And in general, if I've got Y and Z in X, this does not imply that the ordered pair YZ is in X. It did imply that the unordered pair, YZ here, sorry, def X here, the unordered pair is in def X. That's okay, right? But recall that the ordered pair, this is this here. So you should check your understanding here. Y and Z may be in X, and that'll mean that this and this are in def X. That doesn't mean that this whole thing will be in def X. It's definable from something definable. So in general, we won't have this. For some X's, this will be true, but in general, this won't necessarily be true. So this is an aside, right? It's not part of the exercise. Right? I'm just pointing that out. So we're done here. Yeah, we finished those parts there of that question. Okay, don't know if there are any queries there. Okay, let's just pick out some others then. So again, this is more about understanding than mathematics, I think, this one. Says kappa is strongly inaccessible. Okay, so recall what this meant. This meant that it was a regular limit cardinal, but more than that, the strongly part meant that it was kind of closed under power sets. So it's a regular limit cardinal, right? But also, and this is the strongly part, if gamma is a cardinal, if gamma is less than kappa, then 2 to the gamma is less than kappa. Right, so this is the cardinality of the power set of this ordinal. Verify that V kappa epsilon, right, all the axioms of ZFC are true in V kappa epsilon. Now, I mean, you may be forgiven for wondering, well, what on earth is he asking us for here? But actually, there's quick things that can be said here. If kappa is strongly inaccessible, right, we saw that this implied, right, that, well, V kappa equals H kappa, but also all the axioms of ZFC held then in V kappa. This was lemma 248. So the relativizations, all the axioms hold in V kappa. But that's not exactly what this says, right? But it's close, and that's what the correctness theorem tells us. So recall the correctness theorem. So that said, if you had if W is a transitive ZF minus model, and maybe I've got some things there, some gadgets inside W, then for any formula phi, if I relativize the formula to W, this is true if and only if that assignment makes the formula true in W. So this is what related those two different kinds of meaning that we had. Here's the kind of model theoretic, logical, first order meaning. This assignment makes this formula true in this structure. And this is the formula of set theory with its quantifiers restricted to W here. So that's another way of saying phi is true in W. And these are the same things. So all you have to do here is just appeal to the correctness theorem. Well, and lemma 248. Because we'll have this, and by correctness, we'll now have every axiom of ZFC, right, comes out, is satisfied in the structure V kappa. So I think you just have to say that, to say applying the correctness theorem. We have what we want. Down there. So that's this one. Here. Okay, any questions about that? Okay, let me do one more thing then here. And it pertains to what we're doing in the proof of GCH inside L later, is 312, exercise 312. So I've got a structure, for some reason, capital X, and I've got a set of sentences T. Show there is a countable transitive X in which those sentences are true. So, I mean, if you're schooled in logic, this immediately says to you, oh, downward Löwenheim-Skolem theorem, right? And indeed, it gives you that in a hint. Right? So I'm bringing back in the idea of downward Löwenheim-Skolem. So by downward Löwenheim-Skolem theorem, so here's a slight variant on it. For any cardinal lambda, which might be omega, or it might be the size of x. There's no restriction on the size of x here. The downward Löwenheim-Skolem theorem shows there's a y, which is an elementary substructure of x. So any formula in x true about elements from y is true here if and only if it's true here. That's what the elementary substructurehood relation is. with y the desired size lambda. So x may have some enormous cardinality, but for any intervening cardinal number, I can find a structure of that size, whether it's omega or the size of x itself. Okay, so let's choose such a y where y is countable. If all these sentences are true in x, they're going to be true in this y, or with y0. So then the only bit that's missing from here is the transitivity of this y0. But that's no problem. We just use the Mostovsky-Shepardson collapse. So the Downward-Löwenheim-Skolem theorem doesn't guarantee us a transitive y in here. The Downward-Löwenheim-Skolem theorem is about all sorts of structures in all sorts of languages. It's not particular just to set theory. And so it's a theorem in logic rather than set theory. So we apply the Mostovsky-Shepardson collapse. Right? And epsilon, of course, is a well-founded relation, and it's extensional, right, on any structure. So we've got some pi that's going to take y0 epsilon to the x that we want, and it's an isomorphism. And the collapsing lemma said that pi and x were unique. Right. As this structure is isomorphic to this structure, the same things are true here as are true here. So by isomorphism, little x epsilon is a model, satisfies all those sentences T as well. And so we're done. Yeah. Okay. And the Löwenheim-Skolem theorem and these ideas, these will re-emerge in the proof of the generalized continuum hypothesis in L, right, which is kind of why I picked up this exercise.